We begin chapter 2 in section 1 with the derivative and the tangent line problem. Give yourself a hand. We talked about the tangent line problem as being one of the two classic problems back in the prerequisite chapter, and then just a little bit then more in section 1.1. But we're going to get into more detail because from the tangent line problem, we bring up the idea of the derivative. I mentioned that there are two branches of calculus. There's differential calculus that involves the derivative, and there's integral calculus, which will start in chapter 4, which involves the idea of the integral. Now, we know what a tangent is to a circle or even to a curve like I have here, where it looks like looks like a parabola, where it intersects the graph at exactly one point. But what happens if we get a curve where we get a change from going kind of like opening downward to opening upward, and we're looking at that one key value right there? Notice that my tangent line doesn't just intersect it at one point. It kind of crosses it, whereas here it's in the exterior of this curve. Here part of it's above, part of it's below the curve. Or what happens even still when we have a function that looks maybe like this kind of an S-shaped curve, f of x, and we have a point P here where we have this part kind of looking like the traditional idea of a tangent, but yet it still intersects the graph. Well, this is still considered tangent. With respect to a curve, it's a lot simpler, of course, with respect to a circle, but with respect to a general curve, these are all considered tangent to the curve at the particular point P, whether it's this, or this type of effect. Now, to find the slope of a line, we need 2 points, but if we have a tangent line, we have only 1 point, the point of tangency. So to find the slope, we would need a second point, or we would need to incorporate the idea of the limit. All right, so to start off with, we'll use a second point, and our line is not a tangent line, the one here in red. Our line is a secant line. And as you can see here, at point C, we're next to C, which is the point P here, CF of C. This is for the curve y equals f of x. Okay, and then we pick a second point, point Q, not equal to point C, and we make the difference here, not just for convenience sake. I have a point Q having a slightly larger x value. I call it C plus delta x, which means that this right here would be delta x. And the ordered pair would be C plus delta x, f of C plus delta x. And we look at the slope of the secant line. Well, the slope of the secant line would be f of C plus delta x minus f of C all over C plus delta x minus C. It's the difference in the y's over the difference in the x's. We've been finding slope like that for the longest time. The c's in the denominator cancel, and I get this expression, which should look like the difference quotient expression. Now, the trick here is that if we make delta x go to 0, if we move this point Q closer and closer to point P. Let's see if I can do that with my straight edge. And let me get my green pencil here again. I want you to look at the slope of these secant lines. If I can do this correctly. There's one. Actually, that kind of looks like the middle one there. Let's make it a little bit closer here. Let's try to get this one. There's another one. The slopes are going to be slightly different, but the tangent line would be more or less, let's see if I can get it to look reasonable here. Maybe I better use the red pencil again. And you can see that the slope of the green lines are getting closer and closer to the slope of the tangent line here. And how does that happen? We are moving point Q closer and closer to point P by making delta x closer and closer to 0. So as delta x goes to 0, point Q goes to point P, and the slope of the secant line is approaching the slope of the tangent line. So it's time for a definition. Tangent line with slope m. If f is defined on an open interval, let me grab my regular pencil here, on an open interval containing c, and if the limit delta x goes to 0 of delta of y over delta x, the change in the y over the change of the x, which is equal to the limit as delta x goes to 0 of, just what I had back here, f of c plus delta x minus f of c over delta x. If this equals m, and if this exists, then the line that passes through this point with this slope is tangent to the graph of f at that point, which we would refer to as the point of tangency. Now, what this is doing is I'm taking the limit of a difference quotient and I'm getting the slope of the tangent line to the curve at that x value. In this case, x value of c. So the slope of the tangent line to the curve of, to the graph of f at CF of c is also called the slope of the graph of f at x equals c. Now we have definitely talked about the slope of a line. And when we talk about the slope of a line, the slope is the same all the way through. But if we have a curve, then our slope is going to not be the same because of the curve effect as it was in the example that I have up here. But we can talk about the slope of a curve by talking about the slope of a curve at a particular value being the slope of the tangent line of the graph of f at that particular value. So the slope of a curve just means essentially the slope of the tangent line to the curve at whatever x value they give you. All right, so let's jump over here and try an example. All right, here's a graph, or an equation, a function, f of x equals x squared minus 2x. It's quadratic, and the point 33 is a point that's on it. Now, I want to find the slope of this curve at this point, which means I want to find the slope of the tangent line to this curve at the point 33. So to do that, I'm going to go right to the definition. I'm going to take the limit as delta x goes to 0 of f of c plus delta x minus f of c all over delta x. And in this problem, the c is our x value, the x is 3. So this is the limit as delta x goes to 0 of f of 3 plus delta x minus f of 3 all over delta x. Hopefully you can see that okay. Now, I have my function here. This is my rule, so I have to substitute these values in. Here's where it gets to be a little bit of algebra. The limit is delta x goes to 0. Now, if I plug 3 plus delta x in for x here and here, I would get the quantity 3 plus delta x squared minus 2 times the quantity 3 plus delta x minus f of 3. Now f of 3, I plug 3 in here and I get 9 minus 6, which is 3. Makes sense. There's my y value. All over delta x. Now to simplify this, and we did a little bit of this in a previous section, we've got to do a little bit of algebra. We're going to expand this and hopefully this will simplify, and I might even be able to get the delta x factor to cancel. So let's go ahead and go to the next step. This is the limit. A little bit of work here. As delta x goes to 0 of, this would be 3, let's go ahead and square it. I think you know what 3 squared is. 9 plus 6 times delta x plus delta x squared minus, distributing here, 6 minus 2 times delta x minus 3 all over delta x. Take your time here. I squared this out, I distributed here, and as it turns out, there are 3 terms that don't have a factor of delta x, and they combine to be 0. This is a positive 9, a minus 6, and a minus 3. So I get the limit as delta x goes to 0 of, let's see, I have 6 delta x plus delta x quantity squared minus 2 delta x. Well, 6 delta x minus 2 delta x is 4 delta x minus delta x squared all over delta x. I can factor delta x out of the numerator. I get the limit as delta x goes to 0. Now notice here, every time I'm doing this limit step, I write down what I'm taking the limit of. I don't just start simplifying the algebra and skip writing this down. This is part of it until I actually evaluate the limit. So I'm going to factor out a delta x. That gives me 4 minus delta x in the numerator. Look at that, delta x in the denominator. This whole time, if I had used direct substitution, I get 0 over 0. But now, because the delta x's cancel out top and bottom, I get the limit as delta x goes to 0 of the quantity 4 minus delta x. And as delta x goes to 0, this goes to 0, so I get 4. And that is the slope to the curve at that point. That means the slope of the tangent line to this curve at this point. Now, if they want the actual tangent line, they didn't ask for it this time, but you have the point. That's the point of tangency. You have the slope, and you could most certainly write the equation of the tangent line. Let's try another one. This one's a little simpler in a way, although students sometimes struggle with this because of what happens. You'll see that here in just an instant. So I'll go back to this guy. And in this case, this is c, negative 2. So I am taking the limit as delta x goes to 0 of negative 2. So this would be f of negative 2 plus delta x minus f of negative 2 all over delta x. So this is the limit as delta x goes to 0. Now I'm going to substitute this in. It just goes right in there for the x. So it's 3 times the quantity, negative 2 plus delta x minus 5, minus f of negative 2, which looks like it's negative 11. Yep, it's negative 11. All over delta x. Well, let's see what happens here. This is going to be the limit as delta x goes to 0 of negative 6 plus 3 times delta x minus 5 plus 11 all over delta x. Well, a negative 6 and a minus 5 and a plus 11, that's 0 in the numerator. So I have the limit as delta x goes to 0 of 3 times delta x all over delta x. Wow, this is nice. Look at that. So I get the limit as delta x goes to 0 of 3, which we know is 3. Now think about this. I got an answer of 3. This curve is actually a straight line with slope 3. So any point that's on there, if we try to draw a tangent line to it, it's the line itself. The slope is going to be 3. And that wouldn't matter if it was at the point negative 2, negative 11, or at the point 0, negative 5, or at the point 1, negative 2. I'm going to have the same slope because the curve is actually a straight line. All right. Kind of neat. The definition of a tangent line to a curve doesn't cover, unfortunately, the possibility of a vertical tangent line. Because how can you find the slope? A vertical tangent line, a vertical line, has slope that's undefined. So if that happens, if you have a continuous function where you have a vertical tangent line, then the limit as delta x goes to 0 at this particular value, whatever it might be, whatever x equals c is, you will find out that it's vertical by coming up with a limit that turns out to be infinite. It'll either be positive infinity or negative infinity, so keep your eyes open for that as well, vertical tangent lines. Definition: the derivative of a function. All right, mark down the date and the time when you first started studying the idea of a derivative. The derivative of a function is the name that they give to the expression that looks a whole lot like the expression that we just came up with for finding the slope of a tangent line to a curve. It happens so often in the difference quotient, the limit of the difference quotient, that they gave it the name the derivative. Now I can't tell you the history behind that, but I'm sure you can Google it and check that yourself. I have long since forgotten, being an old man that forgets stuff. The derivative of function f at x is given by, now notice it doesn't say at a specific value, just at x, for any value x, is given by, notice the notation, f prime of x, that's how it's read, f prime of x, the derivative of f of x, is equal to the limit as delta x goes to 0 all over the of the difference quotient, f of x plus delta x minus f of x all over delta x, provided the limit exists. Yeah, sometimes the limit exists, sometimes it doesn't. You know, you might get something that's infinite, positive infinity or negative infinity, and it would be unbounded. So for all x for which this limit exists, for which this is true, we say f prime is a function of x. So we take the derivative of a function f, and we're going to get another function. The derivative of the function y equals f of x is kind of like giving us a slope finding machine. The slope of the tangent line at any point on that curve, x f of x, provided that the graph has a tangent line at the point. Now, in the first, or in fact, actually the last couple of examples that I did, we found it at one value. This is going to give us a function, f prime, that will allow us to find the slope at any value. All we'll have to do is substitute in for the x. Now, the word derivative is a noun, okay? When we find the derivative, you can say that we're deriving But deriving sometimes has multiple meanings. So we don't always use the term deriving. We use the term differentiate, or in this case, differentiation being a noun, differentiate being a verb. Differentiate. Okay? Something that's differentiable means we can find the derivative by differentiating, and this is an adjective. So all these words go kind of hand in hand. And notation-wise, besides f prime, you'll see f prime of x, you may also see dy dx, dy over dx. Now that's not like a fraction as much as it is an expression that says you're taking the derivative of your function y with respect to the function x, this being your independent variable. This is known as Leibniz notation or Leibniz notation. So d over dx, don't have the y, so we just write the y value here using the function notation f of x. So d over dx in front doesn't mean times, it means you're taking the derivative with respect to x of f of x. And one that's not used very often, I mean, I remember using it when I was in school, but that was a long time ago, is a big old capital D and then the x below. I think there's some confusion sometimes with this in domain. It kind of looks like the domain of x. But this is saying you're taking the derivative of y with respect to x. That's another type of notation. So, in general, we like to use this one, and we like to use this one. So dy dx is the limit as delta x goes to 0 of dy or of delta y over delta x, which is the limit of the difference quotient, which is f prime of x. This is one that you're going to have to put to memory. Now the bad news right now is to take the derivative or find the derivative of a function, we have quite a bit of algebra to do, depending on how complicated the function is. This is going to ease up in the next section when we get some rules to help us. But we need the definition of a derivative to set up those rules to make our work a little bit more efficient. Here we go. Let's find some derivatives. Now, f of x is equal to x squared plus 3x. F prime of x, can you see that all right? Okay, is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. This is the limit as delta x goes to 0. F of x plus delta x means x plus delta x squared plus 3 times x plus delta x minus f of x, which is x squared plus 3x. Lots of writing. The denominator is just delta x though, so that's nice. I'm going to have to multiply this out. I'm going to have to distribute here, and I'm going to have to distribute here by -1. So I'm going to get the limit as delta x goes to 0 of, this would be x squared plus 2x times delta x plus delta x squared, that's this first part, plus 3x plus 3 times delta x minus x squared minus 3x. Now if you just try using direct substitution, no matter which step, here, here, or here, you're going to get 0 over 0, which is indeterminate. So it's not going to be much help. We need to somehow simplify this and get rid of that factor of delta x that's given us 0 on the top and the bottom. Conveniently, if you look at this expression, and this is going to happen in others, every term that doesn't have a factor of delta x, at least one factor of delta x, cancels. You see the x squared here and the minus x squared? You see the plus 3x here and the minus 3x? So I'm going to kind of combine a couple of steps here. I'm going to write this as the limit as delta x goes to 0. I am going to I have 1, 2, 3 terms. I am going to factor out a delta x in the numerator. That would leave me 2x plus delta x plus 3. These delta x's cancel top and bottom, and this is equal to the limit as delta x goes to 0 of the expression 2x plus delta x plus 3. Well, as delta x goes to 0, this term is unaffected, this term is unaffected, but this is going to go to 0. So I have 2x plus 0 plus 3. This is 2x plus 3. Therefore, 3 dots like that. Therefore, f prime of x is equal to 2x plus 3. Now look at all the work I had here, and that's a fairly simple function. Okay, this gets to be a lot more algebra if, let's say, instead of x to the second power, let's say I had x to the fourth power, because then I would have to take an expression like this and raise it to the fourth power. So it's going to get a little more complicated, and we're going to need a set of rules or guidelines to help us cut down on all this busy work. But we'll do 2 more examples here, and then we'll show you something else that might help on certain types of functions to find the derivative. Y equals 2 over t. Now in this case, my independent variable is t. So what I'm going to do here is I'm going to call it y prime is equal to the limit as delta t goes to 0 of, okay, this would be, this is my function here, so this is what I would be plugging in well, I kind of hate to use the notation. I don't want to mess you up here. Maybe we should call this g of x, or g of t, I should say. So it would be g of t plus delta t minus g of t all over delta t. So just to keep the notation straight here, this is the limit as delta t goes to 0 of 2 all over t plus delta t minus 2 over t all over delta t. Now, you have a complex rational expression. You have fractions in the numerator. I'm going to multiply the numerator and the denominator of this expression here by the least common denominator to kind of get rid of those. And I am going to get the limit as delta t goes to 0. Isn't this fun? Of 2 over t plus delta t minus 2 over t, all that's going to be multiplied by t and t plus delta t. In the bottom, I'm going to have delta t times t plus delta t. You can see what I did was, here, maybe if I underline it here, I multiplied top and bottom by the same expression. So that's going to give me up here, if I distribute, the t plus delta t's cancel, I get 2 times t. Still right in the limit. So that would be 2 times t minus, and then here I multiply it and the t's cancel, so it would be 2 times the quantity, t plus delta t. Now in the denominator, you might be tempted to try to multiply through. Just leave it as is. You'll see why in a minute. Something that you learn either from experience or you listen to me now. Up top, I can distribute. I get the limit as delta t goes to 0 of, now this is 2t minus 2t minus 2 times delta t. Well, the 2 t's are going to cancel. I'm going to combine steps here. I distribute and combine those. That's going to be 0, so I'm going to have minus 2 times delta t. And that's all over, if I can squeeze this in, delta t times t plus delta t. Yikes. The delta t's cancel. Can you see that all right? Hopefully it's still legible. I've noticed in some of the videos it gets a little bit fuzzy, but not so bad. I hopefully it's not so bad for you guys to be able to read this. This is the limit as delta t goes to 0 of negative 2 all over t times the quantity t plus delta t. Well, now and finally I get to a point that if I do direct substitution, I am not going to get 0 over 0. I am going to get negative 2 on top. Down here, as delta t goes to 0, this is going to go to 0, so this is going to go to t, and t times t is t squared. So y prime equals negative 2 all over t squared. And there's the derivative. Again, after we get to the next section, and you see how the rules help us to streamline our work a little bit, you're going to wonder why I made you go through all this. And the reason I'm making you go through finding the derivative by definition is because this is the way some of the problems are kind of set up on the AP exam, so you should become familiar with it. And it's something you study early on, and we don't do a lot of after section 1, but it's something that you're going to need to remember how to do. All right, next guy up involves a radical. So I'm going to find g prime of x, which would be g of x plus delta x minus g of x all over delta x. So this is the square root of, oops, hey, look what I did. Doggone me. Here, I thought I'd go all the way through it without messing up. I forgot to write the limit. And I'm going to be all over you guys about doing this. If you don't write this down, that you're taking the limit each time of this expression. Woof. This is equal to the limit as delta x goes to 0 of the square root of x plus delta x minus the square root of x over delta x. Again, substitution, direct substitution gives me 0 over 0. So I'm going to do a little bit of algebra. I am going to multiply numerator and denominator by the conjugate. That's going to get rid of those radicals up there, the conjugate of the numerator, that is. So I'm going to write the square root of x plus delta x minus the square root of x, and that's going to be times the conjugate, which is the square root of x plus delta x plus the square root of x all over delta x times the conjugate there, which is the square root of x plus delta x plus the square root of x. Now, in the numerator, when I FOIL that out, the O and the I cancel out. I get the limit as delta x goes to 0 of this first one squared, so that'd be x plus delta x minus the last term squared, which would be just x. And you can see the x's are going to cancel. At least I hope you can see that the x's are going to cancel top and bottom. Delta x times the square root of x plus delta x plus the square root of x. Yikes. These cancel, and so now I just have delta x on top, but I also have a factor of delta x on the bottom. So these cancel out as a factor of 1, kind of combined steps here, and I get the limit as delta x goes to 0 of, looks like 1 over the square root of x plus delta x, this is kind of sloppy here, plus the square root of x. Well, as delta x goes to 0, this is going to go to 0, so this is going to be the square root of x, plus the square root of x is 2 square roots of x. And you don't have to rationalize it and put, multiply top and bottom, just leave it in that form. This means that g prime of x is equal to 1 over 2 times the square root of x. Lots of work there. Now I showed you an example of the 3 main types that you'll most likely come across in this particular section when you're finding derivatives. You have a polynomial, you have a rational, and you have a radical. All right, there is an alternate form for finding the derivative of a function, and kind of ties in the idea of something that's differentiable and a function that's continuous, and it's that f prime of x is equal to the limit as t goes to x of f of t minus f of x all over t minus x. That's kind of using that same idea here. Here's x, here's t, and we're going to let t go to x. It gets closer and closer to x, so this point is moving along here to get the slope of the tangent. It's kind of the same idea. I like this sometimes. I actually kind of like this for polynomials, but the reason that I bring this up is, again, it kind of ties together the idea of a function being differentiable, which means you can find the derivative, and a function that's continuous, so there's no breaks or gaps. All right, at a point c f of c, f prime of c is equal to the limit as x approaches c of f of x minus f of c all over x minus c. This is the same thing that I just mentioned to you, except that it is, if I can find my paper that I just set down, it's just that we're letting x go to c instead of t going to x here. We're picking a specific point on the curve. Now, we can also use this and this from the left side and from the right side for one-sided limits. Because if a function is going to be differentiable, say on a closed interval, we'd have to consider the endpoints from the left side and from the right side as we did with continuity. Again, bringing in the idea of how functions that continuous and functions that differentiable are tied together. So a function that's differentiable on the closed interval, if it's differentiable on the open interval, and the derivative exists from the right at a and the derivative from the left at b also exists. If a function is not continuous at x equals c, it's not differentiable at x equals c. And there comes into play my favorite example or counter example for certain things is the greatest integer function. If I look at the limit from the left, or excuse me, from the right at 0, I get 0. Because what happens here, as x goes to 0 here, this becomes 0, and I get the f of x, which is this, all over x, but as x approaches 0 from the right, it's positive. And so these numbers here are both going to be positive, and this is getting smaller and smaller and smaller and smaller. And so what happens here, this is going to go to 0, but this is getting smaller and smaller and smaller. Then this is going to be just equal to 0, because the numerator here is going to be 0. Remember, as x goes to 0 from the right, the greatest integer 0.1, 0.01, 0.0001 is still 0. But here, this is becoming really, 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 really small, close to 0, and it's going to give you 0. Now, on the other hand, if we go from the left side, what occurs here is this goes to -1, because as we go to the left side, -0.1, -0.01, -0.001, as we go from the left side, this is going to go to 0. It's going to get really, really small, but this is going to be -1. -1 divided by a small but negative number, negative divided by negative, is positive infinity. So if it's not continuous at any of the integral values, including x equals 0, and you can see why here, because the limit from the left and the limit from the right are different. So this means, and this is important, put a little star next to this. I'm sorry I kind of rattled through that, but the continuity of a function does not imply differentiability. We have a function here, the square root function, which is continuous everywhere. It's connected, no holes, no gaps. But at 0, we do not have a unique tangent line. Okay? With that stated, this function is continuous, but it's not differentiable at 0. You would have to have a unique tangent line because the slope of the tangent would be the derivative. At this guy here, and I'm not going to probably draw this worth a darn, but it's something like this. At 0, we're going to get the idea of a vertical tangent. It's not going to be a number, a set number. So just because it's continuous doesn't mean that it's also differentiable. However, the other way around, theorem, differentiability implies continuity. If you can take the derivative of a function at x equals c, then you know your function is continuous at x equals c. And that's what I was trying to talk about back here with this guy. So remember, differentiability implies continuity, just not the other way around. If f is differentiable at x equals c, then f is continuous at x equals c. You'd be surprised, or maybe you wouldn't be surprised yet, but this seemingly minor theorem actually comes into play when you're looking at the AP exam. They typically have something that talks about the idea of a function, with continuity and differentiability. So be sure to practice the problems. Like I always say, practice, practice, practice.